Okay, today we're going to talk about dynamic programming. This is lecture 23, EECS 281, winter semester 2020. Start out with our cover slide here. The picture of Richard Bellman, the inventor of dynamic programming, an amazing computer scientist. Something like 600 plus papers written and 39 books, and 100 of those or more were written after he had brain surgery for a brain tumor. So just an amazing computer scientist. If you want some background information, it's a really great idea to go check out the Wikipedia pages. His page is really cool, and also you get a really in-depth, more so than we'll deal with in 281, look at dynamic programming if you read the DP page on Wikipedia. Both great places to get information. So dynamic programming is interesting in the way that its name works. There's a story about how he came up with the name dynamic programming, but it really is kind of a made-up thing. Programming really was a classier way to say planning. So it's not to be confused with the computer programming that we do in CS, but the programming was really about how to plan things. So programming in the sense of television programming is really what that means. And dynamic was a word that was there just to make the whole thing sound special. So it's really cool. It's this primary advantage of typical recursive algorithms is it solves problems that are independent of each other. Dynamic programming kicks in to take over when those subproblems are no longer independent. When we have overlapping subproblems, that's when we can use dynamic programming, as opposed to just using sort of a divide and conquer approach. Some recursive problems don't divide into independent subproblems, so that's when we need to use it. There's a couple of ways to use dynamic programming, which we just call DP for short. We can go bottom up, or we can go top down. So bottom up sort of looks at the smaller cases and keeps solving all of the things it needs to until it gets to the larger case. Whereas a top down solution asks for the final solution and then finds the subproblems that are needed to combine to create that final solution. In the end, both of them end up solving the smallest problems first, because we can't really solve a larger problem without having solved the smaller problems first. But the confusing thing about separating a bottom-up approach from a top-down approach is how it's asked for. If you ask for the smallest until you get to the largest, that's bottom-up. If you ask for the largest and calculate the smaller ones as necessary, that's top-down. And usually we'll see bottom-up approaches done iteratively. You write a loop and you loop until you get to where you want to be. And our top-down approaches are going to be recursive. So you ask for what you need, and then it asks for what it asks for what its needs, and then those things ask for what they need, and so on. When can we do it? DP is applicable if you have a large program that can be broken into smaller subprograms, and the subproblems are not independent. The same subproblems recur, and the more often they recur, the more savings you get from dynamic programming, because you have this thing where you calculate it, and instead of just calculating it, you calculate it and store it. So the next time that you find out that you need it because of the overlapping, you say, hey, well, if I've already calculated this, rather than spending the time to calculate it, why don't I just look it up? So it's one of our classic, let's trade some memory for computational speed. We use more memory in DP, but it saves us speed because rather than doing the calculations later, we just go look things up. How we're going to do this? It's amazing the way that a DP algorithm can take something that's recursive and just terrible in terms of complexity class. I mean, it solves a problem, but it could be exponential. And oftentimes DP will take something down from an exponential down to a linear time, and that's pretty nice. It does cost us more space, so that's the thing we have to deal with. And we have to figure out how to take our problem and divide it into these overlapping subproblems. Sometimes it's very clear. Other times when the problems are pretty hairy, it's hard to see how the subproblems are are easy to be divided, and sometimes how they overlap. So those can be the challenges of DP. The other thing that's a challenge of DP is it's kind of counterintuitive to the way that we think about things generally, computationally. And so I feel like for the first 3 or 4 times I used dynamic programming, I had to relearn dynamic programming. So as you start using it, don't feel too bad if it makes great sense while we're talking about it. You see some examples and you watch somebody do it, and that makes great sense. And then you're on your own, and you can't figure it out. Oftentimes you have to go back and relearn DP more than once. The other aspect of this that we saw on the title slide was dynamic programming and memoization. So memoization is a word that is used almost exclusively with dynamic programming. It has to do with how we're going to use a memorandum. So I usually call it a memo for short. The memo is the area in my dynamic programming solution where I'm writing my previous solutions, so that when I need something, I don't have to calculate. I go look in the memo. So memoization derived from the word memorandum, but it's not quite memorization, because that's not how programs work. So we write things down in the program and then we look them up later. And how this works is right before we exit. Normally we would say, here's the value that I've just calculated. I'm going to return this value. Instead of doing that, right before we exit, we say, well, here's a value that I just calculated. I'm going to write this down in the memo, and then I'm going to exit. One small little step right before the end. And we have to save the inputs as well as the result, because the next time that we come along, we're going to be saying, here are my inputs. Do these inputs match a set of inputs that I've already used to calculate a result? If these inputs match, then I can look up the result, because that's what I do after I rewrite my function to save the input and result on exit. I go back and say, on entry, let's check to see if I've already calculated this. If these inputs have already been seen, then I'm going to return that result. Often this gets done with only minor code changes, and in many cases, because of the way that the memo is structured, memo is a collection of data points, whether it's a 1D collection or a 2D collection or a 3D collection, depending on your problem. But what you do, instead of actually storing the actual inputs, a lot of times you can implicitly store the inputs. So for instance, if I say I pass this in with a value 4, I don't have to worry about storing the 4. If I've got a table and I look in there at index 4, that's where I would get it. So we'll be working on our memo tables there, because they give us a chance to sort of implicitly store the inputs. A lot of times I don't store their values. I just say I can use those values as an index into my memo table and see if I've already calculated this value. So our first example is with Fibonacci. And of course, Fibonacci can be calculated other ways. And in reality, if I was going to calculate some Fibonacci numbers, I would probably not use this dynamic programming approach. There's faster ways to do it. But Fibonacci is something that we all understand and we've seen many times before, and it makes it easy to sort of apply DP to this. So our definition of Fibonacci is this recursive function, and with everything that's recursive, of course, it never works if we don't have a base case. And in this case, there's 2 base cases. There's Fibonacci 0, which is 0, and Fibonacci 1, which is the value 1. So if I use those 2 as my base cases, then everything else can be defined recursively after that by this next line here, where f of n is equal to f of n minus 1 plus f of n minus 2. So anything where f is greater than 2, I can use previously calculated numbers to make that value. So for example, fib 3 is going to be fib 2 plus fib 1, and of course fib 2 is fib 1 plus fib 0. We start to see how there's an overlapping subproblem here, because here in fib 3, I've needed to calculate fib 2 and fib 1. But in order to get to fib 2, I also had to calculate fib 1. In this case, they're base cases, so I still just look them up. But as I start expanding and getting higher up the chain, if I'm trying to calculate something like a fib of 50, I'll see that's a fib of 49 plus a fib of 48. Great. Now as I break that down, say fib of 49 is just fib of 48 plus fib of 47. And fib of 48 is just fib of 47 plus fib of 46. Just about run out of space there. But you can see how there's an overlapping subproblem where if I calculate fib of 47 so that I can get the value for fib of 49, I don't want to have to do all the work to recalculate fib of 47 again when I need to use fib of 47 in fib of 48. There's the overlapping, because if I were to expand this tree downward all the way get down to my base cases, you'll see that I calculate a bunch of these things many, many times. So here's a simple way to write Fibonacci. This find fib is a pretty basic one. It's got my base case there. It's always got to start with a base case in the recursive function. Line 2, which is really 2 lines. If I is less than 1, return 0. So that covers the case when I is 1, I is 0. Oh, sorry, I said that backwards. If I is less than 1, it's going to return 0. We'll see another version that's got this written slightly differently. And if I is equal to 1, I'm going to return 1. So another way to do that, you can say if I is less than 2, return I. And of course, this is implying that this is looking for a number in a sequence. So the value there that's int I, this probably should never be an int. This should be an unsigned int, right? Just because you can't get a negative number in a sequence. You can't have a negative dimension. So here in find fib, we just get our base cases there in lines 2 and 3. If it's 1, return 1. If it's 0, return 0. Otherwise, we just return the recursive call to find fib of I minus 1 and find fib of I minus 2. Very, very elegant looking solution. Very short. It works, but it is spectacularly inefficient, right? It's exponential. We get up to something where we got 1.618 to the n there. And that is a bad number. Anything we're raising something to an n, as n's get big, this gets really big. So it's a golden ratio if you're paying attention. But that's how you could naively write a recursive solution to Fibonacci. And it would work. And like I said, this is exponential in runtime. So this next version is going to use DP. And in this version of the DP solution, it's going to be a bottom-up dynamic programming solution for Fibonacci. Remember I said in dynamic programming, we're going to calculate a value, and then later when we need it, we'll have stored it. So if we try to calculate it again, rather than needing to do all the work, I can just go look it up. So in this driver function here, you see main, which is pretty straightforward. It's just going to run through this loop and calculate the first 100 Fibonacci numbers by calling fib of I here and then printing it out. So it's a really simple function, a really simple starter. But it does end up calling fib here, and that's the function that's going to do all the work here. Next slide. Here is our fib function that's going to return a long 8-byte integer, unsigned, because we never go negative. And right there in line 18, there's a comment that says the largest Fibonacci number that fits in an unsigned 64 bits or 8-byte integer is fib 93. So if I ask for fib 94, I'll have overflow. So in line 19, you see there's a static constant defined that tell us that once we get to 94, we've got to be done, right? So we're going to use that as the size of our memo. And right there is a key fact of dynamic programming. I said the largest one I could calculate was 93, but then I set my size to 94. And that has to do with zero-based indexing. So if I have the ability to calculate the one whose parameter value is 93, then I need a container that's size 94, because the indices on a container of size 94 go from 0 up to, but not including 94, which means it goes from 0 to 93. So if I want to calculate 93, I need to have something of size 94 to stick it in there. And so you'll see that in our dynamic programming. I call it sort of in the dimension that we're dynamic programming. In this case, it's just a scalar. But when we get into 1D and 2D and maybe later some 3D stuff, as you're making successive steps in the programming, in the dynamic programming, you're going to have one extra frame in that direction. So here, since I want to calculate to 93, I need one extra frame, 93 plus 1. So there's my size. I'm going to seed that right away in line 23 with our base case already. 0 and 1 are my first two. And then everything after that gets initialized to 0. That's the way that type of expression works. I've got this static array called fibs of size 94, of course. And it's got 0, 1, followed by a bunch of zeros. That's great because later on I can say, well, if I'm not looking at the first one and the value is non-zero, then I've already calculated it. If it's 0, then it hasn't been calculated. And so that's how this works. Line 26 is a little sanity check. If somebody asks me for a number that is going to cause overflow, I just return 0. Let them figure it out. In line 30, as I mentioned, if something in that fibs thing is not at this first index and it's equal to 0, then that means it hasn't been calculated. So we've got to go calculate it. Oh, I said that backwards. Sorry. If something is non-zero and it's past 0, right? That's a reverse OR operation there. So if fibs of n is greater than 0 and we're not looking at the first one, then we've calculated it already. So let's return that value. All right, got that right. 34 is the straightforward recursive call. Fibs of n is equal to fibs of n minus 1 plus fibs of n minus 2. Right? So that's recursive. I mentioned this was going to be a bottom-up version. This is not a bottom-up version. This is a top-down version. Right? We're recursing. So we're top-downing here, but the way that we end up calling it in a loop from 0 up to 100 sort of reverses the top-down and bottom-up, and we'll make some sense out of that in a bit. But you can see here, if I was to write this simply, all I would need is my base case and a line that returns something like this, which is what our first version of this function looked like back here. Let's get that base case, then return those two things. And then when we said we were going to memoize things, the first thing we wanted to do was, before we returned, instead of just returning the value, let's store the value in our memo. And that's what this does here at the beginning of 34. That says, put this value in the memo because I'm getting ready to return it. I've calculated it. I want to make sure that I never calculate it again. So we store it in the memo, then we return it. After that, we have to come back and add this thing, which has already been done, right? So here we say, if this is calculated already, look it up, don't calculate it. And that's it. That's all there is to memoizing this recursive version of Fibonacci. Right? Next up, here's my bottom-up version of Fibonacci. Find fib BU, bottom-up. And same sort of thing here. This probably shouldn't be an int. This should be a uint 32 or maybe even a size t. If you're feeling good about it. I'll edit these slides later. But we see it's the same sort of thing here. I'm going to set up my base case. And then this version of it, you see that I do have a memo. Right? F is my memo. It has all of my previously calculated Fibonacci numbers. And as I work my way upwards from k equals 2 all the way to whatever I was passed in, then I just look it up. Right? So in this case, the one on the previous page, the first version of it here, we said this was exponential. It's recursive, looks great, works terribly. Here, using a dynamic programming approach, which is calculate these small values, store them, and when the overlapping subproblem reoccurs, look it up instead of recalculating it, this has turned this into something that is clearly linear. There is no trickery about this. There's no recursion. There is just a straight iterative loop that goes from k equals 2 up to I. So that's linear. And so this simple technique of storing the value and using it later as opposed to recalculating it when I need it has changed this exponential algorithm into something that's linear. And that's pretty impressive. All right, moving on. We'll leave fib in the rear view for now. I think we get to check out the binomial coefficient here. We've seen this one already once this semester, and now we're going to really go at it. So n choose m is how this is typically pronounced, and it tells me how many ways can I choose m items from a collection of n items, right? N choose m, and I calculate that n factorial divided by m factorial times the quantity of n minus m factorial. As long as n and m are non-negative integers, this gives me my binomial coefficient. Of course, we start out trying to calculate this, and you're like, well, I can write a factorial calculator. That's no problem. It's a simple little recursive thing. Factorial of n is just equal to n times the factorial of n minus 1. I could write that out, solve for factorial of n, then I solve for n minus m factorial, solve for m factorial, multiply, divide, answer comes out. The problem is factorial numbers are huge. That's why we really don't like factorial complexity, is those numbers are huge. And you can see here that in a small sort of standard int, I can't fit anything in there above 12 factorial. 13 factorial can't even be represented in a standard int. So if I use the long, how much bigger does it get me? Not much bigger. A long is a 64-bit integer, 8 bytes. I still can't even put anything past factorial of 20 in there. If I get into a really big int, a 16-byte integer, I still can't represent 35 factorial. So that's fairly limiting in terms of things that I'm looking at. So, for instance, how do you count poker hands? Well, there's 52 cards and you choose 5 of them. So that would be 52 choose 5. So I would have to calculate 52 factorial, which for this, as this slide demonstrates, I can't store that in any reasonable data type. So there's got to be a better way. This is where our 203 chops come back and we love it, right? The binomial coefficient can be written recursively. As soon as we get something that's recursive, we've got something there. If this thing ends up being recursive and we've got some of these smaller problems that are copies or overlaps of other smaller problems, then DP is going to come to our rescue. So here is another way to write n choose m. Say n choose m is equal to n minus 1 choose m minus 1 plus n minus 1 choose m. So those are two smaller sub chooses, but we can keep doing that. We can keep recursing down and down and down and down and down and down. Of course, recursion never stops unless we get the base cases, which is what we see on the next line. N choose 0, which is equal to n choose n, which is equal to 1. And those are easy to think about. How do I choose 0 things out of a collection of n of them? There's only one way. I don't touch anything. Or how do I choose all n items out of a collection of all n items? There's only one way. I take all of them. So those are my two base cases. And so any other calculation of n choose m, I can use this to stop me recursing. All right? So let's look at this code in a really straightforward way. This is almost a direct conversion of those two equations, right? So here you see my base case. Always start with a base case. If we're going to be recursing, we got to get out first. So if m is equal to 0, meaning I'm not choosing any of them, or if m is equal to n, meaning I'm choosing all of them, there's only one way to do it. There's my base case, return 1. Otherwise, I just return that expression, n minus 1 choose m minus 1 plus n minus 1 choose m. And that's two calls to the binomial coefficient top-down recursive version. So if you look at it, it looks really nice, right? It is very elegant. It looks exactly like the math. The program looks exactly like the math. You have no concerns about understanding what's going on. If you can see the math, you can see the program and make good sense out of it. However, efficiency, absolutely horrible. It's absolutely horrible. It's exponential in a very bad way. So let's see if we can't fix that. This version of it calculates the binomial coefficient from the bottom up. Breathe it in there. We got a for loop inside of a for loop. So without paying a lot of attention to what's going on, if I want to do a complexity analysis of this, I see that the stuff that happens in lines 5 through 9, that's just a bunch of constant time stuff. It's a couple of comparisons logical conjunction there, and some arithmetic. So that stuff is all constant. So I don't really have to worry about how many steps go on inside the inner for loop. All it really matters then is what is the size of my two outer for loops. The outer for loop goes from 0 up to and including m. Now this is a non-standard for loop. Always a time for me to focus closely on what's going on in the code here. So we're going up from 0 to m, and m is included. So this is going to be one more than normal. If I was going to go from 0 up to less than 10, that would get me 10 items. If I'm going to go from 0 up to and including 10, that would give me 11 items. But this should bring you back to what I talked about earlier when I said in the direction that we're dynamic programming, we need to take that dimension and add one more so that we can get to a place that we can look that up. In the end, you see my return value here is return C of mn. So if I want to choose something to solve, like 8 choose 5, right? In the end, I want to be able to look at C at 8, 5, right? So right there, that lets me know that if I made this thing of size 8 and size 5, both of those indices would be out of bounds. So you can see that in line 2, when the vector C is declared, we see that we declare it of size m plus 1, and each one of those vectors has n plus 1 integers in it. So there is my two-dimensional memo. In this case, we're calling it C, and we're going to use this 2 loops out there to figure it out. Right? So we look at the 2 loops. It goes from 0 to m plus 1, really. So there's m plus 1 iterations, and the inside one can go from as small as 0 up to as large as n again. So m plus 1 on the outside, n plus 1 on the inside. Both of those can be simplified to say this is big O of m times big O of n. So my final complexity is big O mn, which is great. We didn't even talk about how bad the one on the previous page was, but we did mention that it was exponential. An exponential versus this linear thing here is not bad at all. So let's figure out how this one works, right? Here's this binomial coefficient helper, and what this one is going to do is calculate this binomial coefficient and stick it in a memo, right? So just like we had on the previous page here, you can see rather than returning this bad recursive call, right? This is a recursive one that's going to go top down, right? So rather than just returning that, I'm going to stick it in a memo first. I stick it in a memo, and then I return it. And of course, in lines 7 and 8, there's my check to see, hey, if this thing is greater than 0, looks like somebody's already written in there, let's go ahead and return that instead of calculating it. So this makes that top-down version much nicer, much faster. All right? See if I can't get a slide to make this happen here. All right. Get ourselves a new slide. Jump into said slide. All right, so let's go at this and choose m. And what I'm going to calculate is something like 8 choose 5. So we can go ahead and do the math on that to get our answer ahead of time. So we'll know when we see it, and we'll be happy that we do. So that's 8 factorial divided by 5 factorial times 8 minus 5 factorial, right? Which ends up giving me something like 8 times 7 times 6 divided by 3 times 2 times 1, right? Cross those out and end up with something that looks like 56. All right, so there's my final answer. And I did that because we could do math. But when we got to write a program to make this happen, calculate this. And so what I need is this two-dimensional vector, right? And you see that I've got my n choose m, and I've got m rows of size n, right? So when I want to write that up, it's going to look like something like m of these things by n of these things. So 0, 1, 2, 3, 4, 5. Remember, we've got to have m plus 1 of them. The same thing here is going to be 0, 1, 2, 3, 4, 5, 6, 7, and 8. So there's what my memo is going to look like. And if you look again at my base case is kind of tucked in here in this loop, lines 5 and 6. If I is equal to j or I is equal to 0, then I'm going to put the value 1 in that location. And so I is going to be going through my rows, and then inside of that, j is going to be going through my columns. So in the case where I is equal to j, what I'm saying is, how do I choose all of them? Or when I is equal to 0, how do I choose none of them? So in this I choose 0 row, right, because here's my i's, here's my j's. In this I choose 0 row, all the i's give me 0. I just did that backwards. It's not 0, it's 1. All right. Clean that up. Try again. All right. So in the 0th row, it's going to be 1. There we go. That's much better. I was already having problems with the math in my eyes. All right. Next time through the loop, we start out with I equal to 1, and we can see that the inner loop starts at I equals j. So j doesn't go all the way to the left anymore. It's only going to go in as, it's only going to start as far out as I gives us a chance. So I'll start here with this 1, 1, and there's not going to be a value there, right? Because what that really equates to is, how do I choose one item out of 0 items? That's not a thing you can do. All right, so when I is equal to j at 1, 1, I also put 1. Then, as I move across, the math that shows up in here says, look for the value that's up 1 and to the left 1, and add that to the value that is in this row, but also to the left 1. All right, that's what those two things say. So that means that this value here is going to be the sum of these two values. All I have to do is just sum them up. I get a 2 there. And every other spot in the entire memo is that exact same relationship. The sum of the items up and to the left 1 and just straight to the left. So I can see this one would add the 1 and the 2 from beside it. So that would be a 3. There's a 4, 5, 6, 7, 8. That's great. That's also an easy row to intuit, right? That's n choose 1. So how many different ways can I choose one item if there's 6 items? Well, there's 6 ways. You take each one of them all by itself. All right. Next time up, we got 2 x's there because we don't start until I equals j, which means I can put a 1 right there. And now I continue to add these things up and to the left. I get a 3 here. This looks like 6. There's 10, 15, 21, and 28. So far, so good? Great. Next row. We start at I equals j. So in row 3, column 3, that's where our first 1 goes. And then we can continue to add and add and add. So I get a 4 here, 10, 20, 35, 56. Those of you who are astute and paying close attention will notice a familiar pattern already. Live lecture, I stop and ask, what is going on here? Somebody usually mouths the words Pascal's triangle, most people being afraid to speak up, but you're right. Pascal's triangle is giving us exactly what we need here. So the binomial coefficient is calculating these things, and we'll see that in the end, we'll end up with the right answer here. So, and I calculate this position, it's 25 there, right? 15. No, there we go. There we go. There's a 35 and a 70. Those of you who are paying attention know that 8 choose 5 is going to be the same as 8 choose 3. So, in reality, there's our answer right now. But we'll get to it in a moment as well. All right. Along the 5 row, those all go away up until I is equal to j. And then I can wrap things up here with a 6, a 21, and a 56. So this is what my loops I and j have done for me. They filled out this memo, and you can see that it's clearly taken me m times n in terms of memory. And all I had to do was write a value in each one of these locations. So it's taken me m times n in time as well. So it's a really nice way that it's done. And then when I get done, I ask for what's in C at, in this case, the indices are reversed. So what's in C at 5, 8? We get the answer, and there's 56. So if, once again, these things were only 8 by 5, I wouldn't have this column, I wouldn't have this row, and I wouldn't be able to get to my actual answer. So hopefully that makes a little bit of sense out of that binary coefficient solution. So let's do some generalization. I already started with this generalization, but we'll recover it now. The general approach in a top-down is to save the known values we calculate. And this is usually the way that we like to do it, because a lot of times the problems that we're solving with DP are recursive. So it's really easy to take a recursive problem and write a recursive algorithm. Recursive algorithms are a lot of times easy to implement, but very inefficient. But we also saw how easy it is to take a recursive algorithm and add a couple of lines here and there and make it DP, because rather than just doing the work and returning it, we can store it and then look it up later. So this is nice, and we haven't really talked about the order of computing subproblems. We'll see that in a little bit as we look at another example here. But the other thing that's important is you might not need to calculate all of the answers to get all of the subproblems. So the last one we did with the binomial coefficient, that was bottom up. If it's got for loops in it, it's bottom up, pretty much. So we're going iteratively from small up to where we're choosing. So that was a bottom-up approach. You say, well, did I calculate things that I didn't need to? I certainly did. Let's look here, and I'll bring out my highlighter, right? And you can see that 56, of course, used this 35 and this 21. The 35 needed 20 and 15. The 21 needed 15 and 6. And this pattern is kind of going to repeat itself all the way up to the top. So to be clear, we could have written this algorithm with a few more checks, a little bit more opaquely, and cut out all of these things. But you can see here that to calculate that 56, only the green items were actually needed. I never used that 70, obviously, because 70 is more than I needed. So this is what I'm talking about when I say that in the top-down approach, we don't necessarily calculate all the values. Because if in top-down, I would say, well, let's start by getting this 8 choose 5. Well, what do I need for 8 choose 5? I just need these 2. What do I need for these 2? I just need these 3. And for these 3, I only need these 3. And for these 3, I only need these 3. So if I had gone top down, it would have calculated me through this green path. The bottom up, as it's written, calculated all of the red numbers. As I mentioned, you could make that bottom up one a little bit savvier to say, don't calculate the entire row. But that's a modification that you once again have to make to the code there. So in the case of a top-down approach, you see that there's some subproblems that need to be calculated in each one of these rows. So when I'm calculating this 20, 15, and 6, sometimes the order of those matters. In this particular problem, it doesn't. But when a top-down approach solution is used, it will get them in the order that it needs them because it asks for what it needs when it needs it, and then lets the temporal thing figure itself out there. So that's what's going on in the top-down approach. It saves us some time by maybe not doing all of the subproblems. Say, well, how can I do that in Fibonacci? Well, Fibonacci is a bad example. There's no way to solve the end without all of the parts of the beginning. So in some cases, you don't need to calculate them. Some cases, you do need to calculate them all. And it is loosely adaptive because it doesn't calculate all the subcases when it doesn't need to. So that's nice. The general approach in bottom up is the opposite of that, of course. We're going to pre-compute the values from some base case, looping our way all the way up to the value that we're needing, right? So the binomial coefficient version that we just looked at, that was, the way that I drew it up was a bottom-up version. It's loosely non-adaptive. We can make it a little bit smarter for that particular one, but not all of them can be fixed that way, right? So a lot of times your bottom-up approach is going to calculate everything from 0 all the way up to hero, and then you get done, all right? Bottom-up DP can be used anytime top-down DP can be used. That's good news. And the time and space requirements for DP can be too large. So this is the reason why we're not using DP in Project 4. You think, well, I did this tree lookup when the points were like this. What if I was just to store all of these MSTs and I wouldn't have to recalculate them over? That would make things faster, right? Yes, it would. However, there are so many different combinations, and factorial of them, that if I've got that much memory to store each one of those previously calculated sequences, I would end up with something that would really be prohibitively large in terms of storing that in a memo. All right. New problem. Started out with Fibonacci. That was a scalar. We were just calculating a single value. Now we're going to something that through binomial coefficient, now we've got this little vector, the n and m. So that was sort of one-dimensional. I needed 2 dimensions to get it, right? So I've got the scalar value in Fibonacci, and I used a 1D memo to calculate it. Now, as I'm calculating this one-dimensional vector of binomial coefficient, I need a 2D memo to calculate it. This next problem, I'm going to be working with how knights move in a chessboard, and a chessboard is clearly a 2-dimensional area. And in order for me to calculate then, I need one more dimension. I need a 3rd dimension in my memo to make that happen. So for a brief recap of how chess works, the knight there in the middle, that's that black knight. Knights can move in any direction, 2 spaces, and then they can turn left or right and move 90 degrees and then move 1 more space. So these 8 gray shadows are all places that the black knight in the middle can move in 1 move. The problem that we're going for is saying, I'm going to move a knight from the top left corner to the bottom right corner of a standard 8x8 chessboard. Can be done in a minimum of 6 moves. It can be done in more, of course, but it can be done in 6. The question is, if I can make 6 moves and get from the top corner to the bottom corner on the opposite side, how many ways can I do it? Okay, well, how could I? Maybe I go down as far as I can and then I go over some, or maybe I go over some and then I go down as far as I can, or some combination of those 2 things in there, and it ends up being quite a large number of them. So we're going to use DP with a 3D memo now, because I have to have a 2D memo just to cover one version of it. After 1 move, I need to know that in 2 dimensions. The 3rd dimension is how many steps. So as I talked about having 1 more frame as it is in the direction of my DP. I said I'm going to need an 8x8 chessboard. I don't need a 9x9 chessboard because there's really still only 8x8 moves in there. But if I'm going to figure out how to do 6 moves in this problem, I'm going to have that 7th step there so that I can go from 0 all the way up to and including 6. So my memo in this case is going to be a little bit bigger. So when we start in the top left corner, that's our red start there. I start there, and you can see that after one move, I can be in either one of these 2 locations, here or here. Great. After 2 moves, I can be in all of these locations. And after 3 moves, it continues to go on, and so you start to see, where does the overlapping subproblem kick in? Well, the overlapping subproblem is right here at this location. Right? Solving for this gray one, how many ways can I get there? Well, if I've solved this problem once before, it's because I knew the answer from here and I knew the answer from there. I don't want to have to recalculate both of these and this every time I use something for any of the places that jump off from here, which would be, this location. I can get to here, I can get to there, and a couple other places that I can get to off screen right now for this example. That one go down there and go down there. That's all places that this one can move to. So the overlapping subproblem is I've calculated how to get there once. Any one of those 8 green X's all need to know how many ways was it possible for me to get to the circled one. So if I can calculate that once and use that in all 8 of those subproblems, I really get some huge savings there. So that's what's going on. I'm going to start out with this memo, and we're going to lose our pretty pictures here. Now we're just going to use numbers. So our knight heads are gone, but what I've got in this checkerboard now is actual values. And I can fit a couple of memos on one screen because the first 2 memos are mostly empty. So you can see there in memo 0 has one way that I can be in the top left corner, because 0 is how many moves I've taken. And so after 0 moves, there's one place I can be, and there's one way to get there, and it's the top left. Everything in these memos that isn't written in from here on through the rest of these slides means that there's 0 ways to do that, right? There's 0 ways to be anywhere here out in the field on the first move, because the first move has to start in the top left corner. So that's what it is. This is 1 filled with a bunch of zeros. After one move, you see that there's one way I can be here and one way I can be there. Everything else that's not grayed out or is blank, that's a 0. So I'll be carrying the previous memo just so we can see it in gray. But one thing to note too is as the knight moves 2 and 1, every time it moves, it changes colors. So it starts out on the blue, one move later it's on white. The move after that, it has to be on blue. The move after that, it has to be on white, and so on and so on. So these grayed out ones are the previous memo. They're really a 0 currently. So there's 0 ways to be at the start after one move, because you have to move away. So I can be here or here. And I say, well, if I can reach a position from here, I'm going to take this value and add it to there. So it was previously 0. Now I add this 1 to it, and it's 1. Same thing here. I go down 2 and over 1. I add 1 to this. And now after one move, I see that there's 2 places I can be. Each of them, I can get there one way. Memo 2. Now I'm going to do 1 memo per slide. So this is after 2 moves. All of the black bolded numbers are places where you can actually be after 2 moves. Breathe that one in a little bit. You can see the previous memo in gray there. Those 2 places where I could be 1. And you can see that anytime I take one of these things, I can take this and see that it can reach here. It can reach there. It can reach here, there. And, oops, I drew that one backwards. That was a bad drawing. Right? That one should have gone. There we go. And there. So those are the ones that value can reach. See that all of them are 1s except the 2 of them that have the 2 in them. That's because this one can also contribute to this location, and this one can contribute to that location. So the two ones from the previous memo both overlap back at the starting point and at that point that's at 3, 3. That makes sense? So then all I'm doing is I'm going to go through this entire board every time I sort of change to the next one and add up every point that can reach every point and fill things in. Right? So here is memo 2 without the memo 1 stuff in there. You can see that's just what memo 2 would be. Everything here that's blank, of course, is a 0. Everything on white has to be 0. And there's some blue places that we can't even reach in 2 moves. As we start calculating memo 3, now you can see that all of these purple locations from memo 2 can reach that location that's in dark red there in 1 move. So if I take all of the values that it took me to get to the purple locations, add them up and say, I can get to this location here 8 different ways. Right? Take my next step, and you see this one is just sort of the mirror image of it. So these two are getting me there in 8. Right? And there is my full memo of 3. And this is the places that I can be after 3 moves. And they're the black ones, of course. The gray ones are still the previous memo. So we can't be on any of the blue spaces. There's a subset of the white spaces that we can be in. And in each space, it tells you how many ways I can move to get to that space in 3 moves. All right. Now we'll just drop the previous memos and just start doing them one at a time here. Memo 4. So let's pick a particular location and see if we can figure out what it's going to be when we fill out memo 5. So I like this one right here. It's just kind of out there in the middle. So all I need to do is figure out which other spaces can contribute to this location, right? And so this one can get me there in 1 move. This one can. This one can. This one can. This one. This one. This one. And this one. So all 8 of those positions can move to that green spot in the middle on the very next move. So to figure out what that value should be there for memo 5, all I have to do is add all of those things up. Right? And it looks like fast math here, 20, 30, oh boy. There's another 70 and 108. That sounds good to me. Let's see how good my math is. 108, sure enough, right? So there's the place that I'm trying to hit, and as I add up all of the places that can reach it, we see that that's the 108 that's there. So that's all we have to do in this solution is fill out the entire grid from all of the places that can reach all of the places, right? And there's our final answer. You can see it. There's 108 different ways to move from the top left to the bottom right using sort of knight mechanics. Right before this, you can see that I could have got that answer by saying 54 and 54. Those are the only 2 that can contribute to here, and that's my 108. Sound good? All right. So you see here, this is memo 6, right? This is me moving 1 extra frame in the direction that I'm programming. I'm programming 6 moves. So I've got to have that 7th frame so that I can go from 0 up to and including 6. All right, let's wrap it up. What's the time complexity for the solution? Well, I have to fill out each one of those boards. Each one of those boards need to be filled out. So there's 8 by 8 in the board, and there's 7 boards. So 8 by 8 by 7. If I was going to generalize this, I would say that it's a board of size n, it's n by m in terms of time complexity. Memory complexity, I got to fill out each one of the boards, so same sort of thing. Let's think about that. Now this is one that we haven't talked about yet, but let's make some sense out of this. Every time I was working on one of these boards, you see that I was taking the numbers in the white and adding them up and putting them in the blue. Right here, I went from blue to white to blue, blue to white to blue. So if you wanted to be tricky about it, you could say, well, I only ever write in one set for a move. If I were to keep one board and just write the whites from the blue on this board and write the next blues from the white on that board, and so on, because we never really use older memos once we get past a full frame in the memo. I shouldn't say older memos. So we never use older frames once we get past an old frame. We just use the previous frame and that's it. So you could take this, and instead of having it be n by n by m in memory, you could have it just be n by n in memory. So that's pretty nice. Say, is that possible in our previous solutions? Absolutely, right? Look at here. As we worked our way through each one of these rows, I calculated this row, and then I used it to get me that row. Then when I got this row, I never again looked at that row. My pencil here, there we go. I never looked at that row again, right? And then as I calculated the row 3, I only used rows 3 and 2. So you can, in many of these cases, reduce your memory footprint by saying, I could do this with 2 vectors of size n, and just add numbers from one vector into the other, add numbers from one vector back to the first, and so on and so on. So the same thing with, of course, Fibonacci numbers. You know that all I need to do is remember the previous 2. I don't need to remember the entire vector. If I wanted to, I could just remember 2, add them together to get the next one, drop one, and so on. So we've got some places where we can get some memory back on these things. In some applications you do that, and sometimes you don't, right? So if I wanted to reliably be recalculating Fibonacci numbers, it would be worth spending the memory to keep them all. Whereas in this board thing, if I was going to calculate where I might be after 20 chessboards, and I never was going to look back at a previous chessboard, it would be smart to save the memory there. So there's my wrap up. Describe the top-down method for this solution. How would the top-down method work? Well, I'd start in this lower right-hand corner and say, well, how many places contribute to this? So all I need to do is solve for these 2. I figure out how many places contribute to them, and so on. I work my way backwards to the top down. All right. So this last couple of slides here, we're wrapping up here. What happens when good approaches go bad? DP is a great approach. However, when the possible number of function values is too high, that means my memo is going to be too large and I can't do it, right? If no good solution is known, it's quite possible that no solution exists. Then, of course, I can't DP it that way. Let's get this thing out of here. We're trying to get done by 6. My summary of DP, it ends up being this advanced technique for difficult problems. We trade space for time, and it only works when I've got these subproblems that are overlapping. So they can't be independent subproblems. The independent subproblem in a binary search, for instance. If I'm looking for a word in a dictionary and I open it to some page, the word is either before the page that I'm on or after the page that I'm on. It's not in both. So that's an independent subproblem situation. But here you saw that calculating fib 5, for instance, would be used by fib 6 and by fib 7. So that's an overlapping subproblem. So we need that. We had to have these dependent subproblems. Bottom up, those solutions are iterative. Top down, those are recursive. And that's how we do it. All right, we'll stop the feed here and we can take things over to the office hours queue if people have some more questions.